Let's talk about precision, accuracy, and how they relate to significant figures. This is something I'm sure you've covered before. Your chemistry teachers from last year assure me that this is what you've covered. It's not particularly fun or interesting, but it is necessary, and it does show a level of understanding and sophistication that most high schoolers don't have. Physics is a science that's going to deal with the real world and therefore real measurements. So you need to be able to express numbers based on measurements or calculations to the correct manner. What's the difference between precision and accuracy? To most people, they mean the same thing, but they're really very different. I got an example here that will help you see the difference. Accuracy refers to how close a measurement is to some sort of true or accepted value. A single measurement or calculation can be accurate. Additionally, if you have many measurements or calculations, you can take the average of those, and they can be classified as either being accurate or not accurate. Think of an archer shooting an arrow at a target. This is the example I was talking about. Each arrow can represent a single measurement or calculation. Accuracy would be how close your arrow is to the target, the center of the bullseye. So here's an example of a shot that's not very accurate. The X represents where the arrow hits. It didn't hit very close to the center of the target. This one looks like it's a little bit more accurate, very close to the center. So hopefully you see the difference between those two. Here's 4 measurements. None of them individually seem to be very accurate. However, the average of the 4 is pretty accurate. The average of these 4 would be somewhere close to the center. Precision, on the other hand, refers to how close a series of measurements or calculations are to each other, with no regard to how close they are to the true or accepted value. A single measurement, therefore, cannot be, by definition, precise. That's okay. Only a series of measurements or calculations can be classified as precise or not precise. Again, think of the archer shooting arrows at a target. The grouping of the arrows would represent the precision. Precise measurements or calculations would show or measure how close all the arrows are to each other. So here's the target again. I've got 4 shots. Boy, those shots are really close together. That means this measurement is very precise. However, the average of these is not very close to the bullseye, so it's not very accurate. Here's another example. Wow, really bad archer here. I've got 4 measurements. They're all over the place. This shows that the measurement is not very precise. However, if I look at the average of these 4 measurements, I'm probably pretty close to the center, so this might be accurate. Here's another graphic to demonstrate exactly what I was telling you before. Upper left-hand corner, I'm not accurate and I'm not precise. The average of the arrows is not close to the bullseye, and the grouping isn't very good. Sorry, that was the upper left. Upper right, I get something that's accurate but not precise. Again, the 4 arrows are all over the place, but the average is probably pretty close to the center. Lower left, I'm not very accurate, but I am precise. The average is nowhere close to the center, but the grouping is really good, so we'd say that's a precise measurement. And then finally, the lower right, it looks like I have something that's both accurate and precise. My grouping is really close together, and the average seems to be right on the bullseye. Why is this so important? Again, physics, and therefore most sciences, are observational in nature. We need observations or measurements, and then we take those to discern or discover patterns and rules that govern how the universe works. So we need to be able to tell something about the quality of our measurements. In experiments, we need to account for the quality of our measurements. This is part of what we call experimental uncertainty. There are 2 parts to this experimental uncertainty. One part deals with the quality of our measurement systems. Sometimes we just have bad tools and bad instruments to measure, maybe like a high school classroom. We don't have a whole lot of money for really good measurement systems. Nonetheless, we do the best we can. Think of a meter stick that somehow got chopped off and is only 90 centimeters long. You may get measurements that are really precise. They all agree with each other, but if your measuring stick is wrong, you can never get an accurate measurement. This is called systematic error. It's something that scientists spend a great deal of time trying to eliminate. We make sure that our measurement tools are up to date and calibrated and well used. The second type of uncertainty is what we call statistical error, and there's nothing that we can really do about this other than repeat the measurements more and more. The nature of science states that there will always be some sort of statistical uncertainties in our measurements. Usually, if we make more and more measurements, the statistical uncertainties will gather around some value. The bottom line is that when we report an experimental measurement or result, we need to report three things. We need to report the value itself. That's usually going to be the average of some number of measurements, or in rare cases, a single measurement. 2, we need to indicate the statistical uncertainty, either expressed as a plus or minus or a percent. Either way is acceptable. And 3, we need to have the appropriate units so we know what we're really talking about. Here's an example. Experiments on Earth for the past 500 years or so have determined that g, the acceleration due to gravity. Let's try that again. Here's an example. Experiments on Earth for the past 500 years or so have determined that the value of g, the acceleration due to gravity, is 9.81 meters per second squared. That's what we'll call the accepted or true value. Let's say we do an experiment in class. We find g, the acceleration due to gravity, to be 10 plus or minus 1 meter per second squared. We could also express this as 10 meters per second squared plus or minus 10%. In this example, we'll assume that our value is an average of, let's say, 8 separate measurements. The value of 10 meters per second can be used to determine the accuracy of the measurement. Since 10 is relatively close to 9.81, we can say that we made an accurate measurement. What can we say about the precision? The uncertainty number tells us about the precision. In the above example, we found a precision of 1 meter per second squared, or 10%. More importantly, we can use the precision of the measurement to quantify the accuracy. Our measurement of 10 plus or minus 1 meters per second squared suggests that we think the true value, or our best value, lies between 9 and 11 meters per second squared. Since the accepted value of 9.81 falls within this range, we can say that our value agrees with the accepted value. Therefore, we have reasonably good accuracy. Let's say we do the experiment again, but this time we find our g to be 9.2 plus or minus 0.2 meters per second squared. This is a more precise result, with the percent error of only about 2.1%. However, we are saying that our best value now lies between 9.0 and 9.4 meters per second squared. This does not agree with the accepted value of 9.81 meters per second squared. This would be an example of a measurement that's precise but not very accurate, since we didn't agree with the true or accepted value. In class this year, most of our experiments will turn out to be reasonably accurate, especially when we measure physical constants like g, but probably not very precise. I expect there to be a lot of systematic error. That's okay. That's just the nature of the equipment we have. We just don't have the money or the equipment to do very precise experiments. That's okay. We'll be fine.